Okay, the final talk of the day will be given by Madeleine Kerr from UC San Diego. Madeleine's studying geophysics with David Stegman and has done a practicum at the National Renewable Energy Laboratory. Let's welcome Madeleine.
Cool. Hi everyone, last talk of the day, deep breath. Today we're going to go to space. We're going to go to the planet Venus. So my talk is on the possible effects of mineral phase transitions on mantle convection in Venus. But before I get into it, we can do like a mini thought experiment. So everyone can, if they want, they can close their eyes and imagine like you're a billionaire. And I know that's hard. And you are looking out, and you've got a spectrometer, and you're looking out at different stars, and you see, oh my gosh, there's a star over here and a star over here, and it looks like they have the same composition as our sun when you look at this, and then maybe the same solar nebula composition. And you're like, oh my gosh, a planet, the same distance as the Earth is from the sun, or Venus is from the sun. What is going on here? Should we go to one of these planets? And therein lies the motivation to discuss Venus versus Earth. Because on the one hand, Venus and Earth have a very similar mass. They are thought to have similar internal structure with a metallic core, on the Earth's case, iron nickel core, and silicate mantle, and they're both like relatively the same distance from the sun. But on Venus, there is no observed surface water. On Earth, we've got oceans. On Venus, the surface temperature is like 740 Kelvin, which can melt lead, so no. Whereas Earth, things are nice. And then on Venus, which, you know, maybe you think this is an important thing, maybe not, that on Venus, instead of tectonic plates that are shifting and causing earthquakes and going under one another, on Venus there's just one big plate. So if you were this billionaire, maybe your name is Beth Jesus or something, you would be like, I need to really know some information about how Earth and Venus evolved differently so I can look at these planets and be like, okay, maybe I'll go to this one and I'll live, or that one and I'll die, which would be really sad for us. So if we think about Earth is a plate-dominated planet where a lot of the things that we understand about heat flow through the Earth is sort of facilitated by the motion of tectonic plates. So you've got this boundary, mid-ocean ridge, where the plates are spreading apart. You've got these, let's see, here it's like two plates sliding against each other. It's a transform fault zone. Here is a subduction zone where this plate is going under this plate, and as it sinks, it sort of entrains ocean sediments with it, and that volatiles makes these volcanoes, so you get these volcanoes like this in South America, or Japan, or Cascadia. But Venus doesn't have the plate tectonics, and we think it's plume-dominated, meaning that the way we understand how it's basically taking heat from the core and ejecting it out into space is mitigated by convection via mantle plumes, or Rayleigh-Bernard convection inside the mantle. Oh yeah, and these are some like overlying, these are like sort of circling these sort of topographic features that we think are associated with plumes on Venus. So here's a brief digression because I'm in Washington, D.C. right now. There's a really cool mission to Venus called Veritas. It's a satellite mission. As far as satellite missions go, it's not the most expensive mission. But so here's like what our topography data looks like for Venus with Magellan. And if we want Veritas, which is this meeting, this is what the topography resolution would look like. So, you know, do we want to be this kind of country or this kind of country? Just asking questions here. So what is a planet like on the inside? Here's a general idea. So we've got hot core. Here it's nothing because it's a boundary condition for me. They've got a cold surface, which is the space or the atmosphere. And inside you've got a mantle, and it's silicate, so it's rock, but it's convecting on million-year timescales, so we model it like a fluid. We've got mantle plumes, which are these red, hot upwellings, and we've got these sort of downwellings here. Yeah, these blue, cold downwelling things. So we can think about a planet as a layered convecting structure with a stiff, cold lithosphere, or, you know, people say crust, but it's like actually part of the mantle is the lithosphere on the outside, and we've got some solid state Rayleigh-Bernard convection on the inside, and we've got a metallic core that's hot. So I think a general principle is that the surface features, we'd like to think that the surface features of Venus manifest the convective dynamics on the inside. So here's a little topographic map of Venus. And we have these sort of two features that I'm curious about looking at Venus. We've got these large volcanic rises, sort of like Hawaii or Iceland, these places where mantle plumes are coming up and impinging on the surface, these large-scale mantle plumes. But we also have these features called corona, and here's a little zoom in of the corona, and they're smaller scale, and we don't have them on Earth. Confusing. There are a lot of them, like over 500. I think the new is like 700. And they're on the order of 100 kilometers across, and they're thought to be formed by a smaller mantle plume, or a thermal or a diapir, impinging on the surface and causing some flexure and generating this sort of circular pattern. So the question is, okay, I showed you that picture of the convecting planet, and I was like, okay, now we have two features that seem to be formed from like Rayleigh-Bernard convection. What is happening inside? What convection processes are causing these two different scales, this 1,000-kilometer scale and this 100-kilometer scale at the same time? Oh yeah, I forgot about this. A little zoom in of corona, some more corona pictures. I'm going to keep shamelessly plugging that. Veritas is great. There's another one called Da Vinci, also great. So thank you to Madeleine for these wonderful things. And you might be thinking, oh, it kind of looks like a crater. This is like 2,000 kilometers wide. This is like 100, 200 kilometers wide, and craters are like really small. They're like this, and they don't look the same as Earth. Anyway, so these are not craters. These are volcanic tectonic structures. So we sort of, we conceptualize this problem as a plume thermal dichotomy, two things, one system. Just to nail it again, got these few large mantle plumes. This region is actually called the BAT region, for the Beta Atlas Themis region. And then we have all of these corona coexisting, adjacent to each other, same system, two scales, what's happening. And this is, a mystery. There have been some conceptual explanations for this. They're like, okay, a big plume comes from the core, very hot. It reaches this transition zone in the mantle where there's a phase transition, and that sort of stalls the plume, and then it creates a thermal boundary layer on top of that plume, and that thermal boundary layer generates these smaller scale plumes, which give us the corona, and then some big ones that can like punch through, maybe like this one, or that's those, like, oh yeah, here's one that can do it. But there haven't really been any models that showed this conceptual image before. But then one day I was like, my advisor was at a conference, I was reading some papers, and we came across this paper that was looking at new ways to model mineral phase transitions in the early Earth, using a new numerical formulation of the mass, momentum, conservation of energy equations that you usually see in sort of geodynamic modeling. And we looked at these little lumps here, and we're like, it looks like, we could maybe get some two scales of plumes. What if we made this more Venus-like? What if we took away sort of the mobility of the lithosphere, made it more stagnant or a single lithosphere like Venus might be, and change the geometries, change the gravities, et cetera, and see what we get. So we ran some numerical models in this geodynamic code called Aspect, and we used a composition of pyrrolite, which is basically, if you imagined the mid-ocean ridge is splitting apart, and as it does that, it's partially melting the mantle below it. And when you partially melt it, you get an enriched phase and you get a depleted phase. And the enriched phase is like basalt, and the depleted phase stays in the mantle. But that origin source that can split into the basalt and the depleted phase is a theoretical composition because we've never actually measured it, and it's called pyrrolite. So that is the composition that we're using. We're using the same as what we would use on Earth. We use new numerical formulations, as I was saying, to model the phase transitions, using entropy as a solution variable instead of temperature, which is really cool and really works well with mineral phase transitions, and we use NERSC. Okay, good time. And so here's what our initial condition looked like with a little temperature perturbation, which we ran it far enough so it didn't really have memory of that. And this is sort of what we got, which was like, whoa. I was very happy when I saw this for the first time. And so we can sort of walk through this model result. First I forgot about this. Mineral phase transitions. What do I mean when I say mineral phase transitions? So on the surface or at low pressures, the pyrrolite composition forms olivine, which is this green crystal structure. And then when you increase the pressure sort of at lower temperatures, so following this black line like this, which is kind of like an Earth-like geotherm or temperature profile with depth, you go from olivine into wadsleyite, into ringwoodite, into bridgemanite, and you have things called endothermic and exothermic reactions, we know this. But if you have a hotter mantle, you're potentially like Venus might have, you could pass through a region with a really large or really broad endothermic reaction. And this endothermic reaction, essentially, what is happening is that Wadsleyite is a less dense phase, and garnet and ferropyraclase are a more dense phase. Thank you. And as you go from Wadsleyite to garnet and ferropyraclase, you are increasing your proportion of the denser phase, you're generating an effectively negative thermal expansivity, and you're causing this layering phenomena to occur. And so, when we look at this model, we can see sort of two scales of mantle upwellings and downwellings. We can get these cold drips. We can get these large mantle plumes, like I was saying, punching through the phase transition and forming maybe the large volcanic rises. We can get mantle avalanches, which are large-scale downwellings, which happens with the accumulation of the cold stuff sort of breaking through and training material along with it. And then we can get these secondary plume features, corona maybe, are formed by these, and that's exciting. So that is the main takeaway, is that partially layered convection due to mineral phase transitions can reconcile possibly the plume thermal dichotomy. And this was a really fun paper working with my advisor. I had a collaborator at JPL. She's amazing. She's actually the project director for Veritas. So that's why, I want the data too, but she's awesome. She deserves it. She's worked so hard. Okay, so let's take this model that we've made and look at other features of Venus to see if there's some interesting connections. So it's changing pace. Baltus Vallis is a canale, not a cannoli. It is a really long lava channel. It's 7,000 kilometers long, and it was emplaced presumably at a short period of time, and since its emplacement, the surface has deformed, maybe due to the mantle convection beneath it, and you can look at the topography changes along this channel, and you can get a picture of, or not a picture, but you can sort of see the undulations of the mantle convection beneath it. This is called dynamic topography, and you're sort of looking at the stress of the mantle convection on the surface boundary. So a cool paper by Conrad and Nimmo, 2003, they basically just did an FFT or power spectra of the wavelength of deformation along Baltus Vallis, and they got sort of 3 peaks that they saw. They identified these are deformation belts. These are crustal phenomena, mountain belts going together. They saw this long wavelength, which is sort of at the limits of resolution, but they're 3,500 mantle depth. But they also saw this other feature that they just did not really ascribe to anything. They were we have no explanation for what this signal could be at the around 640 kilometer wavelength. But when I do my dynamic topography, granted it's 2D, so if it's a full 3D model, it's gonna be different. There's gonna be a lot of things different with the heat flux and the dynamic topography. But you get sort of this moderate wavelength of dynamic topography in our models around the 600, and it's sort of broad. And so when we look at our models, that wavelength roughly correlates to the depth of this upper mantle, the uppermost sort of convective cycle, where you can sort of see these secondary hot plumes and these cold drips are sort of cycling as sort of a mini version of the big mantle convection system. And so we think maybe, we hypothesize, we guess it could be cool if that was, if the Baltus Vallis sort of undulation peak at the 640 area was this upper mantle secondary convective cycle, which would be pretty cool. So overall, main takeaways: mineral phase transitions can happen inside planets and affect the dynamics of solid state convection. A mineral phase transition in Venus is a possible explanation for the coexistence of corona and large volcanic rises, possible because it's a model and we know so little. It's going to come up into the plug later. Mineral phase transitions can affect the planetary dynamic topography, and there's some cool work I'm doing now about the heat flow and interesting things with convection and Rayleigh-Nusselt scaling, which is fun for me right now. And then also we leverage high-performance computing in order to run these large mantle convection simulations. Takeaways, important for me: that country? No. This country, please. This is the Veritas mission, and this is the Da Vinci mission, which is also really cool. They're going to take a parachute with a bunch of mass spectrometers, and they're gonna float it down the atmosphere of Venus 1 hour, and they're gonna collect a lot of chemical information so we can know what the atmosphere of Venus is like, if there's life in the atmosphere of Venus. So overall, Venus and Earth are twins. Venus might be hotter on the inside, and that hotness might generate the secondary scale of convection, and we want to know what's going on inside of her, and in order to understand our sisters and cousins out there in the planet. So yeah, that's the end of my talk. I have wonderful collaborators, but most importantly, I have wonderful friends and peers, and the CSGF has been one of the best parts of my whole graduate school experience. I've met so many amazingly passionate, creative, kind people, and it's, yeah, it's great. And thank you for all of you, and then also the Krell staff and everyone else. Thanks. Yeah. Questions?